Today we are going to learn how to write atomic isotope notations during nuclear decays. Nuclear decay is when the nucleus of an element gains or emits some type of particle smaller than the original nucleus. So the first thing you need to remember from the previous unit is how to write isotope notation and isotope symbol. Remember that in isotope notation, we write the name of the element, like nitrogen, dash the mass number. So this represents the mass of the nucleus with all of the protons and neutrons. We also learned how to write isotope symbol using the symbol of the element, nitrogen, showing its mass number on the top and its atomic number on the bottom. So as long as you remember how to write these formulas, you will be fine as long as you can add and subtract. Put these notes on your periodic table if you haven't done it already. You're going to need your periodic table for the rest of this lesson. This data table can be used on all tests and quizzes from here on out. So fill it in and then attach it to your periodic table so that you have it for the rest of the semester. If you'd like more information on where all of these notes are coming from, they are in the book, chapter 24, section 1, which starts on page 860. So we're going to talk about three types of nuclear radiation: alpha, beta, and gamma. They're represented by the Greek symbols of their name. So in this example, these particles are going to be emitted or ejected out of the nucleus of our isotopes. So they're going to remove themselves from the nucleus. In alpha decay, we lose a helium nucleus from our isotope, which causes our mass number to decrease by 4 and our atomic number to decrease by 2. In beta decay, which is slightly more complicated, a neutron, which very simplistically you can consider to be the bonding together of one electron and one proton to make one neutral particle in the atom. If this neutron were to decay and reject or eject its electron, what would be left would be a positive proton. So we often write the symbol for beta decay as a negative electron, meaning that the change in mass is 0. However, as it is being emitted, your atomic number will actually go up by 1 because a neutron has converted into a proton, and protons add into our atomic number. So when you lose this electron, the neutron changed into a proton, gaining 1 proton, but remaining the same in atomic mass. Gamma radiation particles are too small to be seen and too small to be containing any mass in an atom. And so for this example, in this high school chemistry, the gamma particle has no change in mass and no change in atomic number. And so for the rest of this unit, we will not be writing any formulas for gamma radiation, but it's really good to know what it is in case you decide to watch a movie about outer space and they talk about gamma rays, then you'll know what they're saying. Okay, so you should have gotten a handout from the sub that contains some copies of the notes in the Learning Target packet that we downloaded the other day. Make sure you have the most updated version of the Learning Target packet. Yours should say Nuclear LT Packet 2016. If you downloaded the one from 2015, erase it and download the new one. So let's take a look at some alpha decay in some example problems. Remember, alpha decay is the emitting of a helium nucleus, causing the mass to decrease by 4 and the atomic number to decrease by 2. So we're just going to actually write some basic subtraction and addition problems from here on out. So for example, if you started with uranium-233 with an atomic number of 92, and we were to lose a helium particle, then what would remain? The objects on the right side of the equation should add up to the object on the left side of the equation. So if your original mass was 233 and you lost 4 units of mass, 233 minus 4 should get you 229. And if your original atomic number was 92, but you lost 2 protons, you're now down to an atomic number of 90. Using your periodic table, you can look up this new element, and you should see that it is thorium. Try the next one. Hit pause, try it on your own, and then hit play again and see if you got it right. So if gadolinium-149 ejected a helium nucleus with a mass of 4 and atomic number of 2, you would be left with samarium-145 with an atomic number of 62. Try the rest on your own and see how you do. Alpha fusion is the opposite of fission. So you are literally fusing 2 particles together, or in this case, adding them. And so if you start with something like thorium-229 with an atomic number of 90, and you add a helium nucleus to it, or an alpha particle as it's often known in nuclear radiation, you just add them together. So the masses would increase by 4. 229 plus 4 becomes 233, and 90 protons plus 2 more protons become 92. Now use your periodic table to look up element number 92 and write its symbol on the right-hand side. So this is uranium-233. Hit pause, try the next one, and then hit play again to see if you got the right answer. So if you added samarium's mass of 145 plus helium's mass of 4, you would get 149. If you add 62 protons plus 2 protons, you get 64 protons, which gives you the isotope gadolinium-149. Try the rest on your own. In beta decay, the particle emitted is considered to be an electron. So it has a mass of 0, and because it was formed when a neutron, simplistically, broke apart into an electron and a proton, the electron is ejected from the nucleus, but the proton remains behind. And so your change in mass is considered to be 0 because electrons have no mass. However, that one neutron, which did have mass, transformed into a proton, and so now your atomic number has gone up by 1. This is probably the most challenging of all the different types of decay because of the way you have to think about it. So assume these numbers are like positive and negative when you're adding +1 or adding -1. So for example, I like to write them at the end of the problem. It's just my own personal habit. If you want to write them at the beginning, that's fine too. Whatever works for you. So I like to think about x plus -1, or really it's x minus 1 when I'm thinking about the atomic number of my symbol, right? Because x plus a -1 really changes to -1. So since the mass remained the same, I just copy that same number over, 233. But now I have to do a little bit of thinking. Something -1 equaled 92. So x minus 1 equals 92. My x must have been 93. That's my atomic number. So now I can use the periodic table to look it up, and it turns out to be neptunium. You try the next one on your own and see how you do. Hit pause, and then when you've figured it out, hit play to check your work. So beta decay causes no change in the mass number. So 149 remains the same on both sides of the equation. However, some number of protons plus a negative 1 had to equal 64. If I change these signs to be more simple, x minus 1 equals 64, and then move the 1 over to the other side of the equation to solve for x, I get that x used to be 65. So that's my atomic number, 65. And now when I look it up on the periodic table, I get terbium. Try the rest and see how you do. Not only can beta particles be ejected from a nucleus, they can also be absorbed. So in this next part of the handout, we're going to absorb an electron into the nucleus of an atom. By absorbing this quote-unquote electron particle into the nucleus of an atom, one proton will absorb it and become a neutron. So by absorbing a beta particle, your atomic number decreases by 1 and your mass remains the same because one positive proton absorbed the electron in a very simplistic manner of speaking, neutralizing that proton's positive charge and becoming a neutron. So you've now lost one atomic number because you've lost a proton, but your mass remains the same because a proton had mass, but you lost it, and then you gained a neutron, which equaled each other out. So in this case, I also like to think about it like adding and subtracting with negative numbers. Across the top of the equation, you see that 229 plus 0. So we can keep 229 the same on both sides of the equation. On the bottom, however, it's really like looking at 90 plus a negative 1. And if you change the signs to be a little more simple, plus a negative simplifies to just minus. 90 minus 1 gets you 89. Look up element 89 on the periodic table, and you get actinium. You write this symbol on the right-hand side of the numbers. Try the next one on your own. So once again, I like to look at the problem on the top and on the bottom. So 145 plus 0, the mass remains unchanged. I just copy it over on the right-hand side of the equation. However, on the bottom, I have 62 plus a negative 1. So if I simplify these signs to minus 1, 62 minus 1, I get 61 as my atomic number on the right-hand side, which turns out to be the element promethium, and so I write its symbol next to it. Try the rest. In this last part of the data table, we're looking at these nuclear particles being absorbed. So in the case of alpha absorption, it's a helium nucleus, and when it is absorbed into the nucleus of another isotope, your mass number increases by 4 and your atomic number increases by 2. In beta absorption, or beta capture as it's sometimes known, an electron is captured by the nucleus, causing no change in the mass number as one proton is converted into one neutron. So because you've lost a proton and gained a neutron, your effective change in mass is 0. However, your atomic number has decreased by 1. And gamma radiation, gamma particles are too small to be measured in this exercise, and so we will consider no change in mass and no change in atomic number. So for these next problems, you are challenged to write out the math statement based on the sentence. For example, you've been told uranium-238 is bombarded with a beta particle. So let's draw it out like it's a math equation. In this case, I'll write the isotope symbol for uranium. And then the problem says that it's being bombarded with a beta particle. So I will add 1 beta particle to this nucleus. And now I can just use math, adding and subtracting, to figure out what the new isotope I would form from this nuclear absorption would be. Since there's no change in the mass across the top of the equation, 238 plus 0, I just rewrite my mass. And 92 plus a negative 1 is like saying 92 minus 1, so my atomic number has decreased to 91, and my new element is protactinium, symbol Pa. Try the rest. Your teacher has an answer key, so if you'd like to check your work, check it out with them. Also, make sure that you have downloaded the most updated copy of the Learning Target packet for this unit. It should say Nuclear LT Packet 2016. If you downloaded the one that says 2015, delete it and go back to Schoology and get the most updated one. These notes came from that packet, and tomorrow we will use them for an exciting, delicious activity. See you tomorrow.